Sonar, or sound navigation and ranging, which is what the acronym Sonar stands for, right, is a technique that uses sound waves to map or locate objects in water. It's widely used in marine navigation and fishing, where pulses of sound waves are emitted, bounce off objects, and return echoes that are then analyzed to determine the distance, size, and shape of an object. Interestingly enough, bats use similar processes known as echolocation to navigate and interpret their surroundings. Bats emit high-frequency sound waves from their mouths and noses, and these frequencies of sounds are typically well above the range of human hearing, so they would really range from 20 kilohertz to over 200 kilohertz, where 1 kilohertz is equal to 1000 hertz. So this isn't a math video, so don't really get too deep in the weeds, but just keep that unit in mind. After emitting these ultrasonic sounds, the waves travel through the air, bouncing off of objects, and then returning to the bat as echoes. Bats have highly adapted ears which are capable of detecting these echoes even in noisy environments. And the shape and positioning of their ears help them pinpoint the direction and distance of objects with remarkable accuracy. When these echoes return, bats process the information extremely quickly in their brains to construct a detailed map of their surroundings, and the time it takes for an echo to return helps the bat determine how far away something is, while the pitch of the echo can indicate the texture and density of the object. So this is some really cool, superpowers, or animal superpowers, if you will, right? And similarly enough to nature, ultrasound imaging uses the same principle but adapts it for medical use to visualize internal body structures. So how does ultrasound technology work? Ultrasound imaging and ultrasound technology involves high-frequency sound waves that a handheld probe emits. These waves travel into the body and reflect off of tissue at different rates depending on their density and composition. When these sound waves bounce back to the probe, they create echoes that are captured and interpreted by the ultrasound machine. The precision of these echoes, both in clarity and timing, is crucial because they determine the quality of the image that is produced. Because the more accurate these echoes, the clearer and more detailed the ultrasound images are, which is essential for diagnosing various medical conditions by providing intricate views of tissues, organs, and even blood flow. The receiver in the ultrasound machine plays a critical role here because it interprets these echoes such that it can produce visual representations of the internal tissue. And it also distinguishes between the different densities and compositions, allowing for healthcare providers to differentiate between what is fluid-filled structures, soft tissues, and even more solid masses. An advanced feature of ultrasound technology would be Doppler ultrasound, which specifically measures changes in the frequency of echoes caused by the movement of objects such as blood cells. And it is this method that is crucial for assessing blood flow and identifying vascular issues, such as inflammation. Now, with color Doppler, it takes this whole concept a step further because now we're adding color to the echoes, enhancing the visualization of blood flow dynamics in real time. So the probe would essentially interpret it like this. Blood that's moving toward the direction of the probe, where the emission is coming from, is usually displayed in red, and blood moving away from the probe is shown in blue, with variations in color intensity indicating the speed of the blood flow. Now, you may be familiar with this concept in physics when it comes to the Doppler effect. And the Doppler effect is a phenomenon identified by Austrian physicist Christian Doppler in 1842. You see, Doppler initially proposed this effect while studying the behavior of sound waves and observing the change in frequency and/or wavelength of light and sound as the source of that light or sound moves relative to an observer. So in this case, the observer could be the probe itself that's, emitting the echoes and it's bouncing off of the red blood cells and coming back. Then you can kind of get the understanding of the Doppler shift here, right? Or maybe you've probably experienced this yourself when the sound of a passing siren changes its pitch as it moves towards you and then away from you. In astronomy, the Doppler effect helps in studying the movement and properties of stars and galaxies. And finally, more relevant to the channel, in medical imaging, Doppler ultrasound is critical for diagnosing and monitoring the flow of blood and other fluids within the body, and it allows us to detect abnormalities in the cardiovascular system or any sort of vascularized structure. And we can't forget that it's also used in radar technology as well as weather forecasting to measure wind speeds and to track storm movements, which all of this goes to show how, yeah, this is some pretty cool technology. We'll also touch on this concept later on when it comes to ultrasound technology, but I'll just bring it up here very, very briefly. When you look at an ultrasound image, you probably see that it's just a collection of black and white pictures, right? I want you guys to keep this in mind and maybe what the black and white aspect of an ultrasound image entails. And keep in mind how in ultrasound technology, you're emitting a sound wave and that sound wave has to bounce back off of something. So try to correlate that and think what that possibly entails when it comes to the coloring of a particular ultrasound picture. So keep that in mind because it's going to be relevant very shortly.